In this video, we're going to talk about reaction quotient and how it can be used to determine a shift towards equilibrium. So we're going to start by looking at what is a reaction quotient. So the reaction quotient is represented by the letter Q, and it's a measure of the relative concentrations of products and reactants in a reaction at a given time. So if we consider kind of our standard reaction that we've been using to date, so AA plus BB forming CC and DD. So we've stated previously that the equilibrium constant for this reaction can be calculated by multiplying the equilibrium concentrations of the products raised to their coefficients and dividing by the equilibrium concentrations of the reactants raised to their coefficients. So what we're not writing in here, but we could, is that these are equilibrium concentrations. So this is when the reaction has already reached equal forward and reverse rates of reaction. Q is going to be calculated in nearly the exact same manner. So it's going to look like the same calculation. And the reason that it looks like the same calculation is because it allows us to then compare Q and K. But unlike K, these are just concentrations at a given time. So they're not necessarily at equilibrium. And so we can compare Q and K to determine which way a reaction will proceed to get to equilibrium. We are going to be comparing the values of Q and K to interpret which way our reaction will shift to reach equilibrium. So I've represented the value of Q and K as kind of a bar graph. The taller the bar, the bigger the value. So we see K is constant, which makes sense for a given reaction, and the value of Q is changing depending on where in the reaction we are. So by comparing the relative heights of these two boxes, we can talk about which way a reaction will shift. We're going to start in the middle here, where Q is equal to K. Since Q is measured the same way as K, if the two are equal, this is a system at equilibrium. And so no shift will occur to reach equilibrium because it's already there. If we go to the left, we see here that Q is less than K. This system is not at equilibrium. So as a reminder, both of these values are calculated by looking at the concentration of the products raised to their coefficient over the concentration of the reactants raised to their coefficient. And so if Q is too small, it means that we don't have enough product yet in our reaction. And so the reaction is going to have to shift right to produce more product to reach equilibrium. If, on the other hand, Q is much, much bigger than K, or Q is larger than K, if we go back to our reaction, so we know that this is not at equilibrium either. And if we go back to our equation at the top, what we'll see is that because Q is much bigger than K, we have too much product in our reaction system. And so we need to shift left to get rid of some of those products and reduce the value of K. So this is going to shift left to remove product to reach equilibrium. And we would use a Q value if we had the initial concentration of all of the chemical species in an equilibrium.